In the previous class, yesterday, right, we finally introduced all Maxwell's equations, right? So for Maxwell's equations plus Lorentz force, they form the foundation of electromagnetism, right? So you remember this. For Maxwell's equations plus once you attach Lorentz force, which is the electric force plus magnetic force, then these form the foundation of electromagnetism. It means that you should be able to describe or explain any phenomena in the world of electromagnetism using these 5 equations. You don't need anything else. That's the foundation, right? And so when Maxwell managed to write them down, okay, combine, right, modify the last this equation, right? So and then he started playing with them. He was a brilliant theoretician, right? So he started playing with them, right? And he started combining this equation. You see, we have one equation for the electric field and here one equation for the electric field, right? So we have 2 equations for the electric field and 2 equations for the magnetic field. This one and this one, right? 2 equations for the magnetic field. So he decided, right, let me combine these equations. 2 equations for the electric field and 2 equations for the magnetic field. For the situation when there is no any charges in space and there are no any currents in space, right? And so he combined them and he started, okay, it's chapter 31. And so he ended up, after combining 2 equations for the electric field, he ended up with this equation. First surprise, because back then, 150 years ago, they already knew, they were well familiar with this equation. This is the second order partial differential equation. At some point you will learn how to solve these equations, right? Most of you are not familiar, but we don't have to solve them here, right? But anyway, it's a second order partial differential equation, and he knew that solution of this equation is a traveling wave equation. The equation which we discussed yesterday in the second half of the class, right? You remember we practiced finding all those quantities and so on. So that is the solution of this second order differential equation. But in this case, what creates this wave, traveling wave? What oscillates creating this traveling wave? Electric field in the y direction. Electric field oscillates in the y direction, creating some kind of traveling wave which propagates along this axis, along x. Wow. Moreover, right, he of course combined 2 equations for the magnetic field, and he ended up with, surprise, surprise, similar equation for the magnetic field. But now magnetic field oscillates in the z direction, again second order partial differential equation, but magnetic field oscillates now in the z direction. But this again is a traveling wave which is formed by the magnetic field, and this magnetic traveling wave formed by the magnetic field propagates along also x direction. So it looks like we have 2 traveling waves. One is formed by the electric field, the other one is formed by the magnetic field, and they both propagate along the same axis, x-axis. And it's not over. So look, number of times he was surprised, right? He also knew that in this equation, an equation like this, the factor, this factor, in front of this time derivative, it's a square of the speed of light, the square of the speed of this wave, right? So it means that this wave and this wave, they have the same speed, because you see factors are the same, 1 over mu naught epsilon naught, 1 over mu naught epsilon naught. So it means that these 2 waves propagate with the same speed, and that speed is constant, because this speed is formed out of universal constants, mu naught epsilon naught. So that speed is some kind of new constant. Wow. So of course he started calculating. Of course he knew mu naught epsilon naught, right? So he took a square root of that, and then of course reciprocal. And at this point he wasn't just surprised, he was shocked. I'm sure that he was deeply, deeply shocked. Shocked to such a level, right? You know, with a good excitement. I don't know. I guess if he would if he had a weak heart, he would have a heart attack, probably, right? Because what? Again, back then, people already knew with reasonable accuracy the speed of light, 3 times 10 to the power of 8 meters per second. And from here, he is getting speed of light, that these two waves, these two traveling waves, propagate with the speed of light. So, of course, at this point, he had no doubts that light is an electromagnetic wave. Because what we have here, we have electric and magnetic wave propagating together. It's an electromagnetic wave, and it travels with the speed of light. At this point, he has no doubts that the nature of light is an electromagnetic wave. And he was the first person in the world who came to this realization, who realized that light is electromagnetic wave. So pretty much at this point, you remember yesterday I told you that back then people thought that there are 3 different worlds: world of electricity, right? Then world of magnetism and the world of optics. First, world of electricity and magnetism were combined, right? They created the union. They created the union, right, of these 2 worlds, right? And then, after uniting it, after this unification, so now they annexing the world of optics, because now, since light is electromagnetic wave, so we got these equations from the Maxwell's equations. Since light is electromagnetic wave, it means that everything in optics is just a part of electromagnetism, right? It's basically part of electromagnetism. So all the optical phenomena can be explained using Maxwell's equations, right? So optics is no longer an independent country, right?
I have a question.
Okay, yeah.
Do X-ray and gamma waves travel at the same velocity as light?
Yeah. We will talk about that in a few minutes, right? So yeah, we'll get to that point, right? So yeah, but of course you're absolutely correct. So now let me show his sort of expression, right? Yeah. So I found that picture. Right? So yeah, that was a really shocking conclusion, because up to this point, no one thought that a light is actually just electromagnetic wave, right? So Maxwell did it first. So what after this, right? So let's write down the solution of this partial differential equation, this partial differential equation. Again, at some point you will learn how to solve them. It's not that complicated, right? But you need to know tricks, right? So when you solve the first one, of course, you will end up with the traveling wave equation, which now we're quite comfortable. That's why I asked you to watch a video, and yesterday we practiced half a class playing with this equation. But now it's a traveling wave equation formed by what? By the electric field. And the electric field oscillates in the y direction and propagates. You see that x? And you see that minus, it means that this wave propagates in the positive x direction. Now you should be able easily analyze this traveling wave equation. Except for, you see there is no initial phase. Because usually light electromagnetic wave frequency are reasonably high, so usually researchers are not interested most of the time. Of course, not all the time, but most of the time people are not interested in the initial phase. Right. Okay, so that is the traveling wave formed by the electric field. Of course, we can get exactly the same, okay, not exactly the same, similar. We can get similar equation from the second partial differential equation. And of course, that will be a traveling wave created by the magnetic field. But now magnetic field, you see the subscript. Magnetic field oscillates in z direction, but propagates, as I just told you, still in the same x direction, in the positive x direction. So you see, these two fields, electric field and magnetic field, oscillates in perpendicular direction. Electric field, let's say this is y direction, magnetic field in the z direction, but they all propagate along the same x direction. And another interesting thing, look guys, look at the x and time dependence of both of these waves. Do you see any differences? They're exactly the same. Sine kx minus omega t, sine kx minus omega t. It means what? It means that these two traveling waves propagating together, they oscillate in unison, basically, right? In unison. So remember, it's very important. So once you know x and time dependence, for example, for the electric field, right? So you can write x and time dependence for the magnetic field easily, because it's just exactly the same, right? And so now, since we're experts in analyzing traveling waves, right? Since we practice, now you can use all those tools which we discussed yesterday, right? So of course those are amplitudes, right? So then k is our wave number, which is basically spatial frequency, right? And we introduce it as 2 pi over lambda. If you see that factor in this traveling wave, you should be able to get information about the electric field immediately. Not electric field, wavelengths. You can get information about the wavelengths immediately, right? Then omega, it's angular frequency, right? Introduced in exactly the same way like k. So here we have 2 pi divided by spatial periodicity. Omega angular frequency was introduced in a similar way as 2 pi divided by the temporal periodicity, which is the period, right? So again, if you know omega, you can get a period of the wave like that, right? Easily. Right. Then again, minus between these two terms indicates that this particular wave propagates in the positive x direction. So direction of propagation is over here. If we had here, for example, z, it means that it propagates in the plus z direction. If we had here y, it means that wave propagates in the positive y direction, right? Don't forget that, because that's the typical place for lots of mistakes most of the time, right? Okay, so that's the direction of propagation. And another interesting thing, these two amplitudes, electric field amplitude and magnetic field amplitude, they are connected. That's another surprise, right? So if electric field and magnetic field, form electromagnetic wave, then their amplitudes are connected. And they're connected through the speed of light. First, let me say that, of course, as usual, also speed of this wave can be found by, you remember we discussed yesterday, by mixing a temporal quantity and spatial quantity, right? Omega divided by k. Or you can also find it by multiplying wavelengths and the frequency, or by dividing wavelengths and the period, right? And now what I just said, the amplitudes are actually connected. So it means that, you see, E naught, amplitude of the electric field, equals to the speed of light times amplitude of the magnetic field. Which amplitude is larger? Speed of light is gigantic. It means that electric field amplitude is way larger than amplitude of the magnetic field. It's relative to the magnetic field amplitude. It's just basically gigantic, right? Yeah, I can easily write that the 8 orders of magnitude different, but I cannot imagine that. Seriously, I cannot imagine that 8 orders of magnitude. It's a gigantic difference, right? So remember that. And of course, all these can be derived, right? So all these equations can be derived, right? So it all can be done mathematically, right? And I did it only once. When I started teaching this course, I remember first time in summer of 2014, and I just followed the book, right, to get these equations, right? And it took me probably like half an hour of diligent application of calculus, right? Carefully drawing geometry, right? And students were sitting and looking at me with round eyes. Are you completely nuts, right? Maybe I was, maybe I still am, right? But anyway, so after that, I decided, you know what? For engineering students, it's not worth of dragging them through those calculations, right? Physics major students, yeah, it makes sense, right? In physics, everything must be actually derived. If you have if it's a theoretical course, for example, right? But here I decided, no, it's not worth of those troubles. If you want, you can read the book. All right. So pretty much during that derivation, this naturally appears, this relationship between amplitudes. But I'm just presenting as facts which you just need to remember it. So anyway, so you see, if you have, for example, information, if you have, for example, this traveling wave, right? Electric field traveling wave. Then writing the second traveling wave is a piece of cake usually, right? If you know everything over here, you can write traveling wave for the magnetic field like that easily. Right? Okay, so remember, of course, the relationship between amplitudes, right? Sometimes students forget, right? Or sometimes on the exam I can give a problem about finding an amplitude of the magnetic field, and the amplitude of the electric field is given. And students just grab the amplitude of the electric field and write it as an amplitude of the magnetic field. No. For your level, you should be doing this, right? Okay, so anyway, at this point, we should be comfortable analyzing these traveling waves, and we will do it in a second. Not in a second, in a few minutes. Now, so we real. Oh, sorry. I just pressed my flipper too much. All right. So now we came to the conclusion that yes, from the Maxwell's equations we can get electromagnetic wave. Now let's just draw the picture to see it. It's good to visualize everything, right? It's part of the learning process. All right. So if you draw that, you will see something like this. First of all, let's start with the coordinate system. You see, x-axis is horizontal, and you remember our both of those traveling waves propagate in the x direction, in the positive x direction. So that's what we have here, right? Then you remember electric field oscillated. We had E sub y, subscript y. So it means that electric field oscillates in the y direction. Okay, so we see these red vectors. They oscillate along this vertical axis, y direction. And of course, z-axis is sort of out of the board, out of the screen, right, towards you. And that's where magnetic field, and along that direction, magnetic field oscillates, right? Magnetic field oscillates, right, along z direction. So that subscript b sub z, that's z, indicates that magnetic field oscillates in a z direction. Okay, then what is effectively this? You remember, again, in the video which I asked you to watch before we analyzed traveling waves, you remember we had two types of graphs, snapshot graph and history graph. What is that? Because basically what is this? It's effectively two traveling waves propagating together. So this is, of course, it's a snapshot graph. If we had a camera which could take a picture of an electromagnetic wave, of course, no one has that, right? So yeah, we would be able to see something like this. But of course, actually, it's out of scale, because you remember electric field is 8 orders of magnitude stronger than the magnetic field, right? So of course, this electric field will be somewhere in the skies. Okay, then, of course, this is the amplitude, because, not the amplitude, wavelength. This is the wavelength, because again, it's a snapshot graph, and in the snapshot graph, the distance between crests, okay, here you see we have crest and crest. Distance between crests is the wavelength. And of course, exactly the same distance between crests of the magnetic field, right? This and that. So wavelengths, of course, the same. And another thing which is very important, electric field oscillates in the y direction, magnetic field in the z direction. They perpendicular, and direction of propagation x direction. So you see all these three directions mutually perpendicular. Okay, I cannot do that, right? So, but anyway, all these three directions you see mutually perpendicular, and it's not by accident. In any electromagnetic wave, all these three directions must be perpendicular. If in your picture they are not perpendicular, there must be something fishy with your picture. Again, I mean picture of some process phenomena, right? So they must be perpendicular to each other, period. Right? Don't ask me why. Actually, yeah, I can draw the picture of how electromagnetic wave conceptually generated, and we can see that they are perpendicular. But anyway, let's say in this way. God created nature in this way. They are perpendicular, these three directions. Right. Okay, then. Now, something really amazing. Let me put, okay, let's imagine that we are sitting over here, for example, on the x-axis, right? And just sit there without moving, and let's just observe these waves. These fields, electric field and a magnetic field. Right. You know what I should have also mentioned before discussing this. All right. So these are examples of timid. What it flew out from transverse. Timid traverse. Traverse, it's different. Transverse, right? So you remember longitudinal and transverse waves, right? So this is the example, right? So because electric field oscillates in the direction perpendicular to the direction of propagation, and magnetic field also oscillates in the direction perpendicular to the direction of propagation. So this is the example of a transverse wave. Right, electromagnetic wave is a transverse wave. Okay, now back to this Garfield sitting here and observing what happens to this electric field and the magnetic field. Let's start with electric field. So you sit here, right, and watch what happens to the electric field. So what actually happens to the electric field? Of course, since electric field wave propagates that direction, so first, as you sit here, electric field becomes stronger, right? So you see, so here first electric field weaker, then it gets stronger and stronger, and of course after this point it starts getting weaker again. But anyway, what happens to the electric field? It changes. It changes in time, right? Right. So now, what happens when electric field changes in time? It's a previous class. It's a previous class. You remember when we followed the step of Maxwell when he modified Ampere's law, we added that displacement current. And what is actually inside of that displacement current? The fact that changing in time electric field produces magnetic field, generates magnetic field. Where is that magnetic field? It's this magnetic field, this blue. Right? So this electric field generates magnetic field. Oh my God, right? So something which sounds so strange. Then let's now look at the magnetic field. Again, we still sit at the same point right over here, and now let's look at the magnetic field. What happens to the magnetic field with time? So since this wave travels in the positive x direction, of course, magnetic field first this weak, then getting stronger, strongest, and of course, strongest will be at this point. And then, of course, it starts getting weaker and weaker and weaker. But anyway, magnetic field also changes in time. Then, according to the Faraday's law, which we discussed like 3 or 4 classes ago, what happens when magnetic field changes in time? Electric field is generated. Again, where is that electric field? It's this one, the counterpart, this electric field. So you see, electric field changing in time produces this magnetic field. Magnetic field in its own turn changing in time and produces this magnetic field. They regenerate each other. I generate you, you generate me, I support you, you support me, and we can travel forever and ever. And that's why it's the most self-supporting system I've seen on the face of the earth, on the face of the universe. I don't know, right? And that's why electromagnetic waves travels through the space pretty much since the Big Bang, right? Then let's look deeper. They also, look, they reaches, because you remember I told you, they oscillates in unison, these two waves. So it means that they reaches maximum at the same point and at the same time. They feel like zero at the same point and at the same time, and they reach its minimum at the same point and at the same time. They pretty much shares ups and downs completely. It's the most amazing system, right? Couple of electric and magnetic field, right? So they support each other, regenerate each other, they share ups and downs. It's the happiest couple on the face of the universe, or on the face of the world, right? And they will never quit, and they for example, magnetic field will never tell to the electric field, you know what, you're boring, right? You're not making me laugh anymore, I'm leaving you, right? No, they support each other, they stay with each other all the time. It's the happiest couple. It's the example of a true love, right? So guys, if you want to find the true love, go into optics, right? So because this amazing system exists in optics. It's the most amazing system for me in physics, right? So it's the most supporting, self-sustainable system, right? Yeah, light electromagnetic wave. Yeah, it's an amazing. Right, so now next, and of course Maxwell was the first one who realized that light or electromagnetic wave can exist at different frequencies. And also he realized that they realized about the existence of this whole electromagnetic spectrum. You just asked the question about this. Yes, all these electromagnetic waves, okay, on this side is basically you start with radio waves, right? And on that side, gamma rays, right? They all electromagnetic waves. They all travel with the speed of light, but of course with different frequency and different wavelength. But you remember, speed equals v equals lambda times f, lambda the wavelengths, f frequency. So lambdas and f's frequencies are different, but when you multiply them all the time, you're supposed to get the speed of light 3 times 10 to the power of 8. So now if you start from this side, radio waves, they have long wavelengths. It can be meters, 100 meters, kilometers, right? So wavelengths can be very long, right? Large. But frequency are very, very small. So if you multiply this wavelength frequency, you will get speed of light. So radio waves propagate with the speed of light. Then if you go higher, right, so let's say microwave, the wavelengths become smaller, frequency becomes larger. If you multiply, it's still speed of light, right? So then infrared part of the spectrum over here, again, wavelengths becomes even smaller, frequency becomes larger. Again, if you multiply them, you will get speed of light. Visible part of the spectrum is very, very teeny tiny part of this whole electromagnetic spectrum, right? So, and again, now wavelengths is about 400 700 nanometers, right? So wavelengths getting even smaller, frequency becomes larger, and again if you multiply them you will end up with the speed of light. And then next above that it's ultraviolet, right, radiation, then x-ray again, wavelength becomes even smaller, frequency is oscillating like crazy, but again if you multiply wavelengths times frequency you will end up with the speed of light. And gamma rays, it's even frequency is gigantic, right, but the wavelengths is teeny tiny, right? So, and again if you multiply them you will end up with the speed of light. Electromagnetic spectrum, these are all electromagnetic waves, right? And of course, light, what we mean by light? Light, it's usually, we mean this visible part of the spectrum, right? But anyway, so Maxwell realized that it's not just that part of the spectrum is electromagnetic wave. He just realized that it's much broader, right? Yeah, he was brilliant theoretician. Yeah, so now, from now on, you need to remember in the problems, whenever the problem says that there is electromagnetic wave, no one is going to remind you that if it's electromagnetic wave, it has a speed of light. You need to, your brain should click immediately, and you should be able to realize immediately that it propagates with the speed of light. It has a speed of, the speed is the speed of light. Because I saw almost every semester on the final exam, some students would ask me, so what's the speed? What's the speed, right? So, and I remember I couldn't tell them directly, but I would just keep showing this electromagnetic wave. It's electromagnetic wave. Maybe those students just didn't come to classes, right? But anyway, so whenever you see electromagnetic wave, it should trigger your brain immediately. It travels with the speed of light. It doesn't matter it doesn't matter if it's a radio wave, microwave, infrared, light, visible light, or gamma ray or X-rays. They all travel with the speed of light. Right? Amazing nature. All right, so now after this, let me look at one example, and then we will start. We will move towards interference, right? So I don't want to go. Of course, we can talk more about light, electromagnetic waves, about polarization, and so on, right? But the semester is getting closer to the end, right? Okay, so let me switch to the whiteboard, and I will look at one example. Okay, I prepared the picture in advance. Right. So we have electromagnetic wave. It's not a problem from the book. I just made it up, right? I remember I offered for students to work in a class, but now I just decided to use as an example. So we have electromagnetic wave, EM, electromagnetic wave, and it propagates in a vacuum. Of course, if it's not a vacuum, then of course speed of light will be smaller, right? By the index of refraction. Then we know, according to the picture, you see, that electric field, traveling wave, electric field oscillates in the x direction. Magnetic field oscillates in the y direction, basically horizontal plane. And both of these waves, or we can say one electromagnetic wave, both of these traveling waves, they all propagate in the positive z direction. Actually, I didn't show this direction of this speed. Let me show that. Okay, let me use green. So let's say this is speed, right? Okay, velocity. So it propagates in the positive z direction. Also, you see the amplitude of the electric field, 9 volts per meters. Again, I drew them like a three-dimensional picture, but you see that they are perpendicular to each other. And we also know that the frequency of this wave is 1.510 to the power of 8 hertz. It's 150 megahertz. 150 megahertz. Right? So basically what I drew, it's a snapshot graph of electromagnetic wave. Of course, if we could take a picture of electromagnetic wave, right? And so now we need to find a few things, a few quantities describing this electromagnetic wave. And then I want to write basically a mathematical expression describing the traveling wave of the electric field and traveling wave of the magnetic field, right? So let's do it. So first, part A, we need to find wavelength. Wavelength. And of course, you see, I'm not talking about, for example, frequency of this wave, or that wave, a traveling wave. Of course, electric field and a magnetic field, they oscillate in unison. It means that their behavior in space and time exactly the same. So it means that frequency, they share the same frequency, they share the same wavelength, they share everything the same, except for they oscillate in perpendicular directions. That's one difference. And the second, of course, amplitudes are different. But of course, we can relate amplitudes because they are related to the speed of light. Otherwise, the rest of the parameters are exactly the same for both traveling waves, E and B. Okay, so that's why I wrote just F without saying, is it F of electric field or magnetic field wave? Right. And now the same with the wavelengths. So how can we get wavelengths? The problem is, actually maybe not so, yeah, actually yes, the problem. We have information, it's a temporal quantity, right? It's a temporal quantity, frequency. And now we want to get spatial quantity, which is basically spatial periodicity, right? Spatial periodicity. Basically a distance over which wave reproduces itself. So how can we move from information about temporal information to quantity which describes something in space? Through the speed of light. Okay, through the speed of the wave, right? You remember we talked about that yesterday when we analyzed traveling waves. So now we can use the same arguments over here. So speed works as a bridge between temporal quantities and spatial quantities. Like in this case, we have temporal information and we want to get spatial information. Speed of light helps us. Right? Okay, so okay, the formula, so let me write, so first equals V equals lambda F, right? So first the formula, and of course now we want to get lambda, and it will be C over F. Of course, I switch V to C. Of course, you remember C is basically a convention. In order, if you want to emphasize that this is the speed of light, so we use C. You remember that, you know that. All right, and so pretty much now we just need to plug it 10 to the power of 8 meters per second divided by 1.5 times 10 to the power 8. Wait, hertz, it's 1 over seconds, right? You remember hertz, it's just basically inside of hertz 1 over seconds. Seconds gets cancelled and we will get what? 3? No, 2 meters, right? Yeah. So the wavelength is 2 meters. So it's somewhere in the radio waves, right? So we're talking about a radio wave. Okay, so then part B, we need to find wave number. K. You remember yesterday we introduced it. Wave number, just recall the definition. It's a 2 pi divided by spatial periodicity. And spatial periodicity wavelengths we just found, right? So K, by definition, it's a 2 pi divided by lambda. You see, pretty much it's exactly the same like what we did yesterday, except for now a few things must be remembered. That these two traveling waves perpendicular to each other and their amplitudes are related. And the rest you see pretty much simple questions like for 30 seconds. 2 pi divided by lambda, so it will be 2 pi divided by 2 meters, so it will be what? Pi and inverse meters. So that's the value of K. Now what's next? Angular frequency. Pretty much, you see, I'm trying to find all quantities that we need in order to write traveling wave equations for E and B. That's what I want to get at the end. So, of course, we need K, then we need omega. You remember Kx minus omega t, right? So A, B, C, now omega, angular frequency. It's not W, it's omega, because I see sometimes students just write W. It's not a crime, but it can be a little bit confusing. Usually omega. So omega, by definition, it's a 2 pi divided by temporal periodicity, period. Period right now we don't know, but we know the relationship between the period and the frequency, right? They're reciprocal to each other, right? So we can, let me remind this, so that period equals to 1 over f. So as a result, it will be 2 pi times f. And the frequency is given and was given from the very beginning. So it will be 2 pi, so it will be, you know what, I will probably leave it in terms of pi. So it will be 3 pi times 10 to the power of 8, right? Yeah. 3 pi times 10 to the power of 8, and that's omega radians per second. Right. So now we found omega, and now we almost are ready to start writing down the traveling wave equations, right? Probably first, yeah, let me first find magnetic field amplitude. A, B, C, D. So now, what about B naught? And I told you, not many, but some students made this mistake. So whenever I ask the problem, I give a problem like this on the exam, the final exam. When students get to this point, they just rewrite amplitude of the electric field. I don't know how can you take amplitude of the electric field and use it as an amplitude of magnetic field, but I see it almost every semester. No, but we need to remember that electric field and magnetic field amplitudes are connected to the speed of light, right? So as a result, it means that we can write so B naught equals to E sub 0 divided by C, where of course C speed of light. Again, as I told you, once you know one of the amplitudes, you should be able to find the other one like that. So this is 9 volts per meter divided by 3 times 10 to the power 8 meters per second, right? So it will be 3 times 10 to the power of negative 8. 3 times 10 to the power of minus 8, of course, Tesla. Okay, and now let's write mathematical expressions for the electric field and for the magnetic traveling wave. So A, B, C, D, E, right? So yeah, now we need to write mathematical expressions. Let me start with electric field or magnetic field. Let's do electric field. So E. Okay, on purpose I skip. Okay, maybe I can write T. And then, of course, electric field amplitude. Where is my amplitude? Yeah, it was given 9 volts per meters. Then sine K. What is K? This pi x. Oh, now what is it correct? On purpose, I skipped over here because I didn't want to write it immediately, and I wanted to discuss it. And okay, is this correct? X, okay, over here, this variable must tell us along which axis waves propagate. Along which axis our waves propagate, and of course electric field propagate along z-axis. So over here must be z. X is correct. Students develop this, and I developed for a strong habit, right? And I wrote X. No, we have to be careful, right? X here is not good at all, and here must be z, right? And here also z, because in this case electric traveling wave propagates in z direction. Then we also know it propagates in the positive z direction, so it means that after that there will be minus, right? And omega t. Omega is this, so it's a 3 pi times 10 to the power of 8 t. Initial phase, forget about initial phase. Its frequency is too large, so nobody usually cares about that initial phase. What else is missing? On purpose, I left this gap. It's very important, and probably this is a point where most of the mistakes are. This subscript next to the electric field must tell us along which axis electric field oscillates. Direction of electric field oscillation and direction of the wave propagation. In this case, they are perpendicular because we have transverse waves. All right? So electric field oscillates, you see, in the x direction, plus x minus x, plus x minus x, right? So electric field oscillates in the x direction. So over here, there must be E sub x. But wave propagates in the z direction. So that's why I put z here. Okay, this is a place for most of the mistakes. Especially over here with the subscript, right? Students usually just, write something which doesn't belong to the problem, to this or that problem, right? Although it's not that complicated, usually it's either given on the picture or stated in the problem. For example, the problem can say, let's say, electric field oscillates in a or in a y direction, right? And wave propagates in the x direction. Then, of course, you should immediately be able to immediately extract additional piece of information about direction of the magnetic field oscillations, because you remember all these three directions must be perpendicular. If y-axis is taken by the by the electric field, x-axis by direction of propagation, then a z-axis will be left for the magnetic field. So magnetic field must oscillate in the z direction only, right? Because you remember all these three directions must be perpendicular to each other. Right? In this case, okay, x is taken by the electric field, z is taken by the direction of propagation, then magnetic field is along y-axis. Okay, but anyway, so that's the mathematical expression describing our electric field traveling wave. Right? So what else? Yeah, magnetic field. Okay, let me finish this. A, B, C, D, E, and F. So magnetic field. So B. Of course, will be T. Then, which subscript do we have to use? Again, it's a subscript is going to tell us along which axis magnetic field oscillates. It oscillates along y. So B sub y. Then, of course, amplitude is 3 times 10 to the power of minus 8 Tesla. Right? And then this space and time dependence exactly the same. So you don't have to think. So just rewrite this factor from the electric field to the magnetic field. Because again, these two waves, they oscillate in unison in space and time. So pretty much this part is exactly the same. So you don't have to think much. Sine pi z minus 3 pi times 10 to the power of 8t. Right. So that's, yeah, and of course here now I can put z. So that's how these problems are solved, right? So again, it's very similar to what we discussed yesterday, right? Analyzing just traveling waves.